Alright, so chapter 5 is all about stereochemistry, which is imagining things in 3D and analyzing molecules in 3D. And so we just got finished looking at cyclohexane, which is in 3 dimensions, and so I figured why should we go to chapter 4 when chapter 5 is again all about 3D. Okay, so we're on to chapter 5, and again, as I said, stereochemistry is a study of three-dimensional structure of molecules, okay, 3 dimensions. And so unfortunately, all we have to relay information right is 2 dimensions. We have paper, we have screens, those are all 2 dimensions. So to be able to really get a grasp on stereochemistry, you have to be able to imagine the molecules in 3D. You have to be able to rotate things in your brain, all that kind of stuff. Unless you do a lot of practice with models, you definitely need to practice with your model kits to be able to survive this chapter. I'm telling you, you're going to need those model kits. Okay, you're going to do a dry lab next week to give you some practice, but you get to use model kits on the tests, so feel free to get a model kit and really practice as much as you can, because you're going to need to be able to conceptualize these things. It's a really imperative skill. Okay, so 3-dimensional structure of molecules. No one can understand organic, biochemistry, or biology without using stereochemistry. It's just true. We care about stereochemistry because it plays a major role in the properties of organic compounds, their reactions, and their effects in the body and nature. I'm actually going to show you guys a short presentation tomorrow more about this, but bottom line too is that the body and nature always knows if something isn't quite right. If the shape of the molecule in 3D just isn't quite right, the body and nature always know, even if you and I can't even tell just based on a simple drawing. Okay. So please recall that isomers are different compounds with identical molecular formulas. Remember at the end of chapter 2 we went over constitutional isomers, right, which had different connectivity, and stereoisomers, which were different in space, right? And so far all we've seen are cis-trans stereoisomers, the trans versus the cis, and those had a double bond. Those are really just kind of 2-dimensional stereoisomers. But remember that their definition, the general definition for a stereoisomer, were isomers that differ in how their atoms are oriented in space. And so now we're going to be talking about 3D space, not just the 2-dimensional cis-trans, okay? We're talking about 3D space, okay? Stereoisomers are the central focus of this handout, and within this heading there are several different types of stereoisomers. So we're going to be really delving into this very deeply, and we really need to start with just some basic definitions so we can begin to really discuss stereochemistry and how it affects things. We're also going to be going over some nomenclature and how to depict these molecules in 3D, and so this is really the fundamentals of stereochemistry in this handout. So first up, chirality. Chiral objects are non-superimposable on their mirror image, and lots of things are chiral, including molecules. Okay, so for an example, a simple example of things that are chiral are your hands. This is why I have the camera a bit higher today to show you guys things. So your hands are definitely mirror images of one another. Just imagine there's a mirror, yep, they're mirror images of one another, but they're non-superimposable, as in they don't stack nicely on top of each other. That's why you can't wear your left-handed glove on your right hand, right? Because they don't line up right, okay? So they're mirror images, but they're not the exact same. They don't stack nicely on top of each other, and that's what I mean by superimposable. They're non-superimposable. They do not stack nicely, okay? Even some gloves, like I said. Here's some sweet gloves that I got, okay? These are mirror images, okay? Mirror images of one another, for sure. Okay, they're mirror images. Just put a mirror right down there. They're mirror images, but they do not stack nicely. Okay, so these gloves are definitely chiral. Okay, conversely, things like spoons. How about spoons? These are definitely, again, mirror images of one another, but they stack nicely, right on top of each other. That's what I mean by superimposable. They just stack, okay? Because they're the exact same thing. You don't need like a right-handed spoon. You can eat with the right-handed spoon with your right or left hand. Doesn't really matter. They stack nicely because they're identical. They're completely identical. And so these are achiral. We're going to see that in just a second. But in terms of chiral things, your hands are a very good example. How about left and right-handed scissors? Handed scissors. Right, it's really hard to use right-handed scissors if you're a left-handed person, okay, because it just doesn't quite fit right. And those scissors, though, are mirror images, and they're non-superimposable. Golf clubs, same thing. They're mirror images with non-superimposable. And shoes. Just like gloves, right? You can't wear your left shoe on your right foot because it just doesn't fit right. They're non-superimposable. So including molecules. Molecules are also chiral. Okay, so here is a chiral molecule. Right there. Okay, if we imagine putting its mirror plane right there, just put a little mirror there. Let's draw its mirror image. Looks like this. We just drew its mirror image. Okay, but if we make these molecules then, I have a little model kit here. So here's that first molecule. The OH is coming at you. Okay, the OH is coming at you. And here is the other molecule. Again, the OH is coming at you, but it's on this carbon over here. The third carbon, if you want to number from the left. Okay, so if I take these two molecules and I try and stack them, I want to try and see if they are superimposable. Okay, well, right now as they are, they definitely don't superimpose. They definitely don't. Okay, here the carbons don't line up. You can see here I have one coming off. So what I want to try and do then is kind of like maybe rotate this one, flip it. Okay, and now let's see if they stack. They do stack nicely, but notice how the OHs do not stack on top of each other. The OHs do not stack. Okay, so again, these are non-superimposable, but they are mirror images. There you go. It's kind of hard to see. They are mirror images, but if I try and stack them, again, if I tried and like take this guy, stack him on top of there, okay, it's non-superimposable. Okay, the OHs do not stack nicely. Okay, we can kind of, if we turned it around, they stack nicely like this, but then I have a carbon coming off that chain there and a carbon coming off over here. Okay, so they, again, they're non-superimposable. As soon as I stack them nicely on top of each other, the OHs do not line up. The OHs are not on top of each other. So these were non-superimposable. But they were mirror images, that's why they are chiral molecules. Sorry, a chiral molecule. Okay? Here is another chiral molecule. Okay, again, if we imagine its mirror plane right there, and we draw its mirror image, okay, so if you took this molecule and tried to stack it on the original molecule, right, you need to like flip it, right, because here's like the OH. In order to stack it on top of here, you have to kind of flip it. But do you see here that if we flipped it, then that OH would be going back and the CH3 would be coming forward. And then it's no longer, it cannot stack on top of the original molecule. Again, try to imagine stacking it over here, stacking it on top. You'd have to like flip this guy, but then once you did the 180-degree flip, right, the OH would be going back and the CH3 would be coming forward. And so again, that's non-superimposable. It cannot be stacked on that original molecule. How about a more complex molecule? This is a bridged bicyclic molecule. Okay, it's got a ketone right there. Okay, I can make this with the model. It's really easy to make it with a model kit. Drawing it in the other direction, it's a little bit hard. Here we go. There's its mirror image. Again, if you tried to stack this guy on top of this guy, you'd have to like do a flat 180 rotation, right? You wouldn't need to flip it like this guy, but if you just did a 180 rotation, right, to try and get the ketone over here, right? If you did a 180-degree rotation, do you see that the ketone ends up down here? Okay, just imagine the 180-degree rotation. The ketone does not end up nicely stackable right here. Instead, it ends up down here, and again, these are non-superimposable mirror images. Okay, and so that's why these are chiral molecules. Each of these guys, they're all chiral molecules. We'll see these guys are all interrelated. Sorry, these are related to each other, and these are these. Sorry, but we'll see that in a second. So conversely then, we do have achiral things, okay? Achiral objects are superimposable on their mirror image, which means they're identical. They're the same exact thing. So good examples of achiral things are chairs. They definitely stack nicely on top of each other. Tennis rackets. Those again stack nicely. How about tube socks, right? Not special socks designed for a left or right foot, but just normal tube socks. And then, as I showed earlier, spoons. Right? Those are identical in every way. They stack nicely. So here's an example of an achiral molecule. Okay, we imagine its mirror image. So really, right, this guy's coming at you and that guy's going away from you. No matter like what angle I draw it coming off of the carbon, this guy's still going back and the other one's coming at you. And so these guys are completely superimposable. So here it is. Here's the OH and the BR. Here's the other one. It's really the same thing. Just right on top of each other. Nice and stackable. Okay, they're the same molecule, even though no matter what angle I've drawn, the BR kind of coming off, whether it's to the left or the right, it's still just always going back. Okay, so nice and superimposable. Because they're identical. They're the same molecule. Same compound. Okay, how about this guy? Okay, draw its mirror image. Yep, you just stack it right on top of this guy. It's the same exact molecule. Superimposable. It's achiral. Achiral. How about one more? OH. Okay. Again, it's definitely just superimposable. You can put it right on top of the other guy. So he is achiral. I haven't been labeling any of these. I'm going to do so now. These guys were achiral. These guys were achiral. Achiral. I'm saying in plural, but they're really kind of the same molecule. These guys. It's one molecule. It's the same. Whereas these guys were both chiral. They're two different compounds. We'll see that. They're related, but they're two different compounds. And these guys are also chiral. Okay, so chiral, their mirror image, non-superimposable. Achiral, mirror image, they are superimposable, aka they're identical to their mirror image. Okay, chiral, non-superimposable. A very good tip for quickly determining whether or not an object or molecule is chiral or achiral is to look for an internal mirror plane. This is called a sigma plane. Okay, look for an internal mirror plane. A chiral object or molecule does not have an internal mirror plane. An achiral object does have an internal mirror plane. Okay, so for instance, we'll go through lots of examples here. This guy, OH. Do you see an internal mirror plane, as in is part of the molecule reflected across the an imaginary mirror plane in the middle of the molecule right onto the other side? I see one. It's right here, right down the middle of the molecule. Right, you just put that right down the middle of the molecule. Yes, the OH is hanging off here, but just put the OH on top. And there's definitely a sigma plane here. Okay, and so this guy is achiral. Okay. How about the one we drew earlier? Okay. There's no longer any like central mirror plane, because if we put the mirror plane right here, then we have this CH3 that's not being reflected over here. We just put the mirror plane right there. Okay, so there's no internal mirror plane here. So this guy is chiral. How about the one we drew just above? Right, do you guys see its mirror plane? Sure, again, it's right down the middle of the molecule. Okay, so this guy definitely has a sigma. So he is definitely achiral, as we mentioned earlier. How about this guy? We drew him earlier as well. Again, no mirror plane, there's no sigma plane. So this guy is chiral. Interestingly though, closely related, but still very different. What if we did this guy? OH, OH. Okay, this one's harder to see, but the sigma is kind of the plane of the paper. Okay, so I'm going to try and draw that. Okay, so if I could kind of draw lines across it. Okay, The sigma is the plane of the paper. Plane of paper. Right? It's kind of cutting right through the middle of the molecule. Cutting right through. Okay? So this guy is indeed achiral because he has an internal mirror plane. Okay? How about this one? Okay. This one also, it's just the kind of the plane of the paper. Sorry. So that one should be, again, kind of the plane of the paper. Just cutting right through the middle of the molecule. So he is again still achiral. How about this one? OH. Okay, so again, if we cut right down the middle, this CH3 needs to be reflected over here, and it's not. If we cut right down the middle. If we cut through the plane of the paper, then this OH is coming up, and there's nothing being reflected on the same side going back. Okay, so this guy is definitely chiral. He has no sigma. No sigma plane. Another cyclohexane though. Okay. CH3. Okay, this time, although I agree that the plane of the paper is still not a sigma plane, because again, if it were the plane of the paper, then we'd need something on going away, another CH3, to reflect that. But if we cut this molecule right down the middle, just right down the middle. Okay, imagine those CH3s actually on a model kit. We could definitely put them right in the middle of that plane. This definitely has a sigma plane, and so this guy is achiral. Sorry, and this guy should be in purple as well. Okay, so look for these internal mirror planes. They will be very, very helpful. Okay, do you guys see it? Right down the middle. Okay, this guy is achiral. And one more. OH, BR. Still don't see any sigma plane. This guy is chiral. Okay, so there's definitely just like an inherent symmetry to the molecule when it's achiral, right? Inherent symmetry. Okay, that symmetry is probably a sigma plane. And again, my best tip is to use model kits. Again, it's really hard to see these things conceptually in your brain in 3 dimensions. But if you get practice actually seeing them with your hands and using them and trying to manipulate them yourselves, you will get better. It will get easier. You do need to practice. Okay, so again, chiral, non-superimposable mirror images, non-superimposable with their mirror image, and they do not have a sigma plane. Achiral, they are superimposable on their mirror image. That's because they're identical and they have an internal mirror plane, also known as a sigma plane. Okay.